we'd like to show that all of the eigenvalues of the matrix which represents G are roots of unity. So this is just the generalization of the observation that if we put a Abelian here...
I think I get it. Well, because if we look at the representation for the identity and the eigenvalues for the identity being 1, but then we say, okay, well, if we have the identity, we can express that as, let's just say this group element and its inverse. We have the representation of the group element and its inverse. We use homomorphism property. No.
No, you're on the right track. So keep talking me through it here.
Okay. So let's get some writing down.
Let's let G be an element of our group.
Okay.
And let's let A, just for the sake of notation, let's let A be the matrix used to represent G.
Okay.
So where do we go from here?
Well, I was actually going from having noting that the eigenvalue for the representation of the identity of G is going to be 1.
Representation for the identity is which matrix?
Is the identity matrix, and the eigenvalues for the identity matrix will be 1.
Okay.
And we can express E as G times G inverse.
G times G inverse.
Actually, I want to say I want to say, and well, because this is a finite group, we know that all elements are going to have a finite order. So, an element G to the n, or we're not using n.
We can use n. I don't know.
We're not repeating.
So there exists capital N, let's say.
Sure, such that G to the n is E.
Okay.
So now we're going to say D of G to the n, which we can express as, because of the homomorphism property.
Yes.
D of G to the n,
Yep.
And if that's I.
So we have A raised to the n power.
Yeah. So
the identity matrix. Okay.
So now we can say, before we had said, okay, well, A is a root of unity.
When A was just a single number.
Well, let's take the, how do I want to say this? Okay, so let's do this. So we can do I minus lambda I for one side, and A to the n minus lambda I, or no, lambda prime I. So I want to kind of do this to both sides, take the determinant of both, see what we get. Is that too much? I'm sorry, that's my natural inclination.
I think it's too much. So let's do this. Let's just subtract identity from both sides.
Oh, and yeah, I mean, we get that there.
And we get the zero matrix.
Yes.
And so A is a matrix which satisfies the polynomial equation. Right, the cyclotomic polynomial equation.
Yeah.
X to the n minus I is equal to 0. But then we have the theorem we talked about last time, the Cayley-Hamilton theorem. And the Cayley-Hamilton theorem will guarantee that if AV is equal to lambda V, actually I don't even think we need Cayley-Hamilton for this. Let's suppose AV is equal to lambda V. Let's then figure out what is A to the NV.
So, let's see.
By the way, Cayley-Hamilton is actually this direction, so we're not going to need it here.
The direction saying that...
Well, the direction that what we're going to conclude will imply that A satisfies X to the n minus identity equals 0. But we can prove what we're trying to imply without the Cayley-Hamilton theorem.
Okay. So let's see. I want to almost say lambda to the n, but
Yeah.
I'm not sure how I would know that.
Well, let's just real quickly say what's a squared v. A squared v is going to be a times av. But av is equal to lambda v.
Mm-hmm. So a lambda v.
Yeah, but lambda is a scalar.
Lambda av.
Yes.
Oh, okay. I see. Yes.
And that's lambda times lambda v.
Okay.
And so forth and so forth. So because
yeah,
lambda is a
okay.
scalar, we get away with that.
Okay. That makes sense.
All right, so far so good.
Mm-hmm.
But now, this implies
That if lambda is an eigenvalue for a, that lambda to the n is an eigenvalue for a to the n.
that's right. Lambda n is an eigenvalue.
And if we
for
have,
a to the n. But what is a to the n?
well, a to the n is equal to I, and well,
I.
the eigenvalue for a to the n or I is 1.
Yes.
So that means for a, it has to be, well, a root of unity.
That's right. Thus, lambda is a root of unity. An nth root of unity for some value of
Yes.
n is an
Which will divide the order of the group,
root of unity.
whatever the order of the group is.
That's right. Yep.
Okay,
There it is.
Very
That's
good.
the proof.
That's a clean.
So, yeah, that's nice. And
Yes.
we didn't even need, interestingly enough, we didn't need to know that A has a certain number of distinct eigenvalues, or we didn't need to know that it was diagonalizable. We didn't need anything other than the observation that G is a finite group, and therefore all of its elements have finite order.
And
The observation that you made about the eigenvalues all being 1 for the identity matrix.
lambda's not necessarily a primitive root of unity.
It doesn't
right?
have to be
No.
primitive, that's right. It just is some root of unity.
Mm-hmm.
So it could be 1. It could be negative 1. It could be, e to the 2 pi I over 17, or whatever. But whatever it is, it's got to be a root of unity. So that severely curtails the kinds of matrices we can use to represent elements of finite groups. That they all have to be matrices whose eigenvalues lie on the unit circle. Not only on the unit circle, they have to lie as a commensurate. They have to be commensurate with 1. So they have to be at some. They have to be at some angle on the unit circle which is commensurate with 2 pi. So that when we raise it to a sufficiently high finite power, it becomes 1.
Okay. Then it goes. Okay.
So when Math Bob, I think, says that the eigenvalues all lie on the unit circle, that's what he means.